Swayam Prabha. Digital India. Educated India.
Hello everyone. So, today I am delivering my lecture of module 1 on the course plates and shell. Now, in the last few lectures, I have given you some basic concepts of the elasticity, 3-dimensional elasticity, and from there I reduced it to a 2-dimensional problem, which will be used for plate analysis. Then I told you about these assumptions in the theory of plate in bending, especially for thin plate, which is popularly known as Kirchhoff-Lap hypothesis for thin plate bending, where the assumptions I have mentioned. Very important assumption is that the deflection is small, it is limited to 1/5 of the thickness of the plate. Then I have discussed another important assumption, that normal to the plane before bending remains normal after bending. That means, length of the normal does not change after bending. So, this indicates that epsilon z in this vertical direction, where the z axis is aligned in the vertical direction, is 0. Then I have discussed the stress strain relationship and how the stresses are expressed in terms of deflection, vertical deflection. Then the stress resultants, bending moment, shear force and S shear for the plate I have derived. After that I have gone to the equilibrium equations of the plate. There I have taken a small element of a plate and have shown the free body diagram of this element under the action of external loading, distributed loading and internal forces that is developed. All internal force quantities, that is the bending moment, shear force, twisting moment, etc., are expressed in case of plate as unit of per unit length. Thereafter, I told you the characteristics of plate equations and how it can be solved in special cases. One of the rare cases I have discussed, that is the circular plate with clamped edges, and general technique for the solution of the plate problem that involves a homogeneous solution and a particular integral. So, up to that we have discussed and boundary conditions that we encounter in a plate of straight edges I have mentioned, and in course of that discussion I have also covered that the slope and curvature of the plate in any direction which is at an angle of inclination alpha with the x axis. Then we have derived the differential operator in the new direction, normal direction and tangential direction. With that knowledge, I think we will be able to apply to some problems that today I have brought for you. Today I intend to solve some problem of based on the lectures that I have delivered in the first modules. Okay. So, what are the problems? Let us see. 5 problems I have brought for you. The first problem is, let us read this problem. For a steel plate whose length along y direction is very large compared to its width along x direction, the deflected surface in that case is assumed to be a cylindrical. The axis of the cylinder is parallel to the length of the plate. At a certain point, the strain in shorter direction was measured as 0.001. Now, taking modulus of elasticity, Young's modulus of elasticity as 2 into 10 to the power 5 Newton per square millimeter, Poisson ratio as 0.3, we require to find the stresses, normal stresses sigma x and sigma y. Okay. So, that is the first problem. Second problem, let us see the slope in x direction and y directions are known as the first derivative of the deflected surface with respect to x and with respect to y respectively. Now, I want to prove, or rather you will be able to show this with the knowledge that you have developed. The maximum slope in a slightly bent plate is given by root over del w by del x whole square plus del w by del y whole square. So, that is two problems. Yeah. Next problem, let us see. We have derived the boundary condition for straight edges. Now, let me derive the boundary condition for curvilinear edge. A plate may have a curvilinear edge, say all the edges may not be perfectly straight line. Okay. For example, you have a quarter of a circle required for any purpose, say for resisting the floor load or live load. Then in that case the two edges are straight, but one edge is curved. Okay. So, we want to formulate the boundary condition along the curved edges for three different edge condition, that is, one is clamped, another is simply supported and another is free. And I want to show the formulation from the first principle. If we can derive the equation from the first principle, then we can substitute our known expression and we can get the full boundary equations after simplification. Okay. Then question number 4, find the expression for the distribution of internal stresses in a plate and show its variation along the thickness with reference to the middle surface. Now, here the internal stresses in thin plate is sigma x, sigma y, tau x y, which other stresses, that is sigma z, then your tau x z and tau y z we neglected, but in general they also exist. So, their influence is small because compared to others, but they are also existing. So, we will try to find the expression for all stress components, and when the thin plate example comes, then we can show that these components are negligible compared to the three component of stresses sigma x, sigma y and tau x y. Okay. Then we will go for one problem that we want to solve exactly, exact solution we want to find, and it is possible because of the boundary condition taken as fixed. So, for that condition, let us derive the expression for deflected surface, and once the deflected surface is found, you can find the expression for moment. Okay. So, let us solve this problem one by one, and if some steps are not completed, you can complete it. Okay. Now, let us see the first problem that I have told you. A steel plate whose length in y direction is very large compared to its width. So, that means, if I have a plate like that, say this is the x axis and this is our y axis. Okay. So, along the y direction the length is very large, such that the plate deforms in the form of a cylinder. Okay. Cylinder. So, deflected surface of the plate is a cylinder. Now, due to this assumption, we can say that epsilon y, that is the strain in y direction, is 0, but strain in y direction we know that from expression is 1 by E sigma y minus mu into sigma x. In this equation, sigma y is the stress along the y direction, normal stress, and sigma x is the stress along the x direction, mu is the Poisson ratio. Okay. Because of this condition, that is this is equal to 0. So, that means we get sigma y is equal to nu into sigma x. So, this equation we will use later on, all right. Now, we are aiming to find the sigma x and sigma y. Okay. Now, let us write the expression for epsilon x. Epsilon x is equal to 1 by E sigma x minus mu into sigma y. Now, since sigma y is given as mu into sigma x, this equation can be simplified as sigma x by E into 1 minus nu square. Based on that, because our measured quantity is epsilon x, given the epsilon x is equal to 0.001. Now, this is given. So, we are aiming to find sigma x. So, sigma x can be found out, sigma x is equal to E into epsilon x 1 minus mu square. So, substituting this value, that is epsilon E is 2 into 10 to the power 5, epsilon x is 0.001 and mu is 0.3. So, 1 minus 0.3 square. After calculation, this becomes 219.7 Newton per millimeter square. Okay. So, once sigma x is found, then sigma y from this relation can be easily obtained. Sigma y is equal to 0.3 into 219.7 and this is equal to 66 Newton per millimeter square. So, this is the answer of this problem based on the stress strain relationship and for the condition that in one direction strain is negligible. So, by that way we could get the result because of this assumption. Okay. Now, let us go to next problem. Next problem, let us see. We have this regarding slope. Okay. So, the problem is that the maximum slope in a slightly bent plate, assuming W is small, is given by under root this dw dx whole square plus dw dy whole square. Okay. Now, let us show the coordinate axis x, this is y. Okay. So, we know the slope in x and y direction. Now, for an element, if I take an element of a plate of length dx and width dy. So, in any other normal direction, say this direction is denoted by n direction, okay, n direction, and other direction perpendicular that is t direction, tangential direction, and say normal is making an angle alpha with the x axis. Okay. So, we express this deflection in this dw is the contribution of this plus. So, we have shown this as in our last classes, that means slope in x direction which is increased by the length delta x and slope in y direction increased by the length del y. Okay. From that we got this del w by del n is equal to del w del x dx by dn plus del w del y into dy by dn. Okay. Now, from this triangle we can see that dx by dn is cos alpha and dy by dn is sin alpha. Okay. So, accordingly I can write this cos alpha del w del x plus sin alpha del w del y. So, this is the expression for slope in any direction. For the condition that the slope in that direction is maximum, we have to use the maximization principle of calculus, that this is equal to 0 at some angle alpha equal to alpha 1, okay, with taking the derivative with respect to alpha. Okay. So, this equation is say 1. Okay. If I take the partial derivative of that equation with respect to alpha, we will get this sin alpha del w del x plus cos alpha del w del y, okay, equal to 0, and alpha 1 will substitute, because I have taken a particular angle alpha is equal to alpha 1, the slope will be maximum. From this equation number 2, we get that tan alpha 1 will be your equal to this del w del y divided by del w del x. So, this equation we have obtained, that is the direction of maximum slope is given by this tan alpha 1, that is the slope direction, alpha 1 is the direction, and we got this as del w by del y del w by del x. Okay. Now, let us see the expression of maximum slope. Okay. Now, if I substitute the angle of alpha in this expression, equation number 1, then we will able to get for that particular direction the slope which will be maximum, because we are imposing the condition. Okay. Now, before substituting this expression, let us first express the tan alpha 1 in terms of sine and cosine. So, tan alpha 1 we obtain that del w by del y divided by del w by del x. Okay. So, suppose this is a right angular triangle, okay, and we have this angle is say alpha 1. So, this is say for example, dw by del y this side, and this side is del w by del x. So, naturally hypotenuse of this triangle is root over del w by del x whole square plus del w by del y whole square. Okay. So, we get this sin alpha as sin alpha 1, sin alpha 1 will be del w by del y divided by hypotenuse del w by del x whole thing square plus del w del y whole thing square. Similarly, cos alpha 1 will get del w by del x and root over under root del w by del x whole thing square plus del w by del y whole thing square. Okay. So, this is the thing that we obtained for this sin alpha 1 and cos alpha 1. Now, let us put in this expression. The maximum slope is given by this. For the particular angle, we have found that it is given as del w by del x cos alpha 1 plus del w by del y sin alpha 1. Now, substituting this expression that I have got here for cos alpha 1 and sin alpha 1, we can see that the denominator of this expression is this. And numerator of this expression will be this. So, one can get from this expression very easily that maximum slope is nothing but root over So, this is proved. So, whatever we have given in the question, it is now proved. Okay. So, we get the maximum slope in the slightly bent plate as the under root of the square of the slope in x direction plus square of the slope in y direction. Okay. Let us go to the third problem. Now, third problem we are having about the boundary condition. Okay. This is regarding the boundary condition, and we will see that the curved boundary condition having the different expression, okay, different expression because of this curvilinear coordinate that is okay, that is necessary to be involved here. Okay. So, here what we mean that actually we have a plate, say a portion of the plate, certain plate, and this is curved, this edge is curved. Thickness of the plate is h as usual. As usual, this is the middle plane, okay, and this is, say for example, this is x axis and this is your y axis. Okay. Now, this length is taken as elemental length dx and dy. This length is the arc length. Now, we define the direction in which we want the derivative or the quantities of moment, okay. And two direction, one is normal direction, that is normal to the edge, and another is tangential direction t, and this normal makes an angles, for example, with the x axis as alpha. Okay. So, that things are given to us, and now we go for deriving the quantities, okay, for this plate, if the edge is clamped, if the edge is simply supported, and if the edge is free. For clamped edge, there is no difficulty. Clamped edge, we have w is equal to 0 and del w by del n equal to 0. Now, in terms of the Cartesian derivative, you can write it cos alpha del w del x plus sin alpha del w del y equal to 0. So, these two equations represent the boundaries along the curved edge if it is clamped. Okay. Now, let us go for the simply supported edge. Okay. Second is simply supported. In the simply supported edge, for example, again I am drawing this curved edge. Okay, this is curved edge. This is the middle plane, all right. So, this is normal direction and this is your tangential direction as usual, all right. Now, it is given that we have to obtain the boundary condition from this first principle. Okay. Now, if you see that along the normal direction, the normal stress is sigma n. So, if I want to calculate, because in simply supported condition, the moment and deflection is 0. So, one condition at the boundary at the curvilinear boundary is w is equal to 0, that is easily satisfied, but second condition is that m n equal to 0, bending moment along the normal direction, that has to be 0. Now, let us obtain the expression for bending moment m n from the first principle. Okay. Now, how m n is generated? M n is generated m n and m n t. M n t, of course, it is not necessary here, but we will still evaluate this. Okay. Now, consider a small element. Small element, say this angle is alpha, all right. This is d x, this is d y, and say this side slanting side is d t. Okay. This side is d t. Now, we have a small element here situated at any point on the plate at a distance z from the middle surface. Then we can write the moment of this element, force on this element is sigma n into area of the element d z into 1, if I take the unit width. Okay. If I take the unit width, then this is the force. So, force into distance z, and if it is integrated from h by 2 minus h by 2 to plus h by 2, we will get the moment along the normal direction. Okay. Now, we have to obtain this sigma n from the first principle. Okay. Now, if you see this condition, then along the edge, which is, if this is your direction x, this is direction y, along the edge where the x axis is normal, say this is your sigma x, and along the edge y axis is normal, this is sigma y. Then you have shear stress in the two faces, tau x y, and another shear stress along these faces, tau y x or tau x y, because these are same. So, let me write tau y x. Okay. So, this is my this element, any element, okay, on the curved boundary, because T t is the for a small element, the curved length and the straight length is same. So, I have taken d t is approximately equal to your curved length. Okay. So, now I want to obtain the expression for sigma x and sigma y when they are resolved in the normal direction. So, expression of stresses, normal stresses along the normal to the plane, inclined plane, tangential plane is sigma n, and sigma n can be found by equating the sum of the forces to 0 along the normal direction. So, that is the principle. So, and of course, the shear stress will also act, shear stress say here tau n t. Okay. So, these two stresses will generate the moment along the normal direction and twisting moment with reference to n and t direction. Okay. Now, let us find out what is sigma n. Now, if you see, if you resolve the forces along the normal direction, what we get, sigma n into d t is the length of this side, slanting side, into h, h is the thickness of the plate. So, this is the force in the normal direction, and this is equal to the component of the force on the x and y direction that we are showing here in the free body diagram of the element. So, I can write sigma x dy thickness h into thickness h, and after resolving it normal direction, it will have the angle cos alpha. Okay. It will have the term cos alpha. Similarly, sigma y and dx into h, and if I resolve to the normal direction, it will have sin alpha. Then we have tau y x, tau y x is acting on the phase dx. So, dx into h is the area, and when I resolve it to the normal direction, it will be cos alpha plus tau x y, it is acting on the phase dy. So, dy into h into sin alpha. Dividing both sides, by your this dth, dt into h, we will be able to get this very interesting expression. We also know this sigma n equal to sigma x cos square alpha plus sigma y sin square alpha plus 2 tau x y into sin alpha cos alpha, because we know from this triangle that dx by dt is sin alpha, okay, and dy by dt equal to cos alpha. So, making use of these two relationship in this expression, we arrive at the normal stress component. Okay. Similarly, if I want to find out the tangential stress component tau n t, which generates the normal the twisting moment m n t is generated by tau n t, and similarly here dz into 1 if I take a unit width of the plate and integrated from h by 2 to minus h by 2, we need tau nt. Tau nt is found after resolving the forces. Say this is my triangular element that I have shown you, here it is alpha and this angle is dt, this is dx, this is dy. Okay. So, this stress is sigma x, this normal stress is sigma y, and there is shear stress tau y x, and there is also shear stress tau x y. So, resolving tangentially along the tangent direction, this is sigma n and this is tau nt. So, tau nt is found after making the equilibrium equations for all the forces that are shown in the tangential direction. So, if I resolve the forces in the tangential direction, then we have tau nt into dt into h, there is the forces in this tangential direction on this inclined face is equal to sigma x dy into h sin alpha. Then we have this minus sigma y dx into h cos alpha plus tau y x dx into h sin alpha and minus tau x y dy into h cos alpha. Okay. Now, divide both sides by dt into h that we have done earlier. So, ultimately we will get tau nt is equal to sigma x, after simplification you will be able to get sigma x minus sigma y sin alpha cos alpha minus tau x y cos square alpha minus sin square alpha. So, the expression for tau nt is now known. So, based on that expression what we described in the previous slide, we can obtain this m nt, okay, by just by substituting tau nt that we have obtained here, okay, in this equation. Now, the boundary condition along the simply supported edge is this is 0 and m n equal to 0. Now, m n that we have got, m n now after this substituting the expression for tau x, sigma x, tau n, sigma n, okay, that we have obtained in the expression of this moment, there you substitute here, okay, you will be able to get m n. So, expression for m n is obtained as very simple term, it is obtainable m x into cos square alpha plus m y into sin square alpha plus 2 m x y sin alpha cos alpha. Why I wrote this term inside the bracket? Because I know the expression for m x, m y and m x y in terms of derivative. So, if I want to write this in terms of derivative, instead of this keeping this as m x, I can write it say minus d and this is cos square alpha plus, and again minus will be there, minus d, then for m y I can write and then this m x y. M x y expression also we know it, that is minus d, okay. Then 1 minus nu, then del square w del x del y, these two will get cancelled. Okay. Now, after rearranging this, you will find that this gives you a very interesting expression mn equal to, you will get minus d and you will get del square w del n square. So, that is the Cartesian derivative del square w del x square into cos square alpha, okay, and then del square w del y square sin square alpha, okay, and then del square w del x del y and your cos alpha sin alpha, that is there in this term. You will get this is transformable in terms of the second differentiation in the normal direction. That operator I have shown you in the earlier classes, you can see these notes. Then with the another terms, that is once you get the second differential operator in the normal direction, second differential operator in the Cartesian direction is obtained only by changing the angle alpha. So, instead of alpha you put 90 plus alpha. Okay. So, you will get operator in the tangential direction. So, you will be able to find this expression is simply reduced to like that. So, m n is having very simple expression like that equal to 0. Now, since the plate is supported along the boundary, okay, naturally there cannot be deflection in the boundary. So, ultimately with the same reasoning that we have done earlier in the straight edges, we have for simply supported edges along the curvilinear boundary is this one condition and first condition is this, second condition is this. Okay. So, this is the condition along the simply supported edges. Okay. Now, when we come to the free edge, then difficulty arises. Now, let us see curvilinear free edge. Okay. Curvilinear free edge has your different obligations, because of the fact that at the free edge bending moment is 0. Okay. So, this edge is free and say this is my x axis and this is y axis. So, along the free edge you have this, if this is taken as a S arc length S. So, q s, there is the shear force along this S direction plus this twisting moment and its derivative with respect to tangential direction. So, we have at any point on the curve boundary we have two direction along the tangent t and normal to the tangent n. So, this is equal to 0 is one condition and another condition is m n equal to 0. Okay. So, first condition is can be easily substituted that we have earlier obtained, but second condition we want to derive q s and m n t is known and the del by del t operator is to be found out. So, in this connection the m n is that we have found earlier minus d Okay. So, this is m n and this is equal to 0, because it is not supported. So, I cannot take this as one curvature is 0, okay, that is not possible, all right. So, we have taken this is m n equal to 0. Second equation is coming from this q s plus del m n t by d t equal to 0. So, that is the S shear, Kirchhoff S shear along the curved edge. So, that means it is not necessary to consider the twisting moment and shear force along the curved edges to be 0 separately. Two effects can be combined to give a single equation. Achha. Now, if I see an element, this is d x, this is d y. Now, here I am telling it say d s whatever may be, and this is my angle is alpha. Okay. So, for the equilibrium, if the force is here, the shear force is here is q y along this edge d x edge, along the d y x shear force is q x and these are taken upwards. So, I can write q s d s equal to q x dy plus q y dx. Okay. That I can write. Now, dividing both sides by ds, we now get q s is equal to q x dy by ds, dy by ds we can write cos alpha, and dx by ds we can write as sin alpha. So, this is the expression for q s and it is equated to be 0. Achha. Now, expression for q s, q x and q y are known in terms of Cartesian derivative, where we have derived earlier q x is equal to minus d, this operator del del x, then del square w, where del square is the Laplacian operator, that is del square del x square plus del square del y square. Okay. So, this is q x. Similarly, q y is minus d del by del y del square by w. Okay. So, these two equations can be substituted here to find the q s. Now, question coming here is coming here del by del t m n t, whereas m n t expression is already obtained. Okay. M n t tau n t is obtained. So, naturally you can obtain m n t, all right. Once you know the tau n t, you can obtain the m n t by simply integrating across the thickness. Okay. So, that is possible, and based on that we can write this the second equation, that is this equation, only knowing this operator. So, q s plus del m n t del t equal to 0. q s we have substituted whatever we got here, and d by dt into m n t. Okay. Now, d by dt is operator, which is actually is found from this. We know that del by del n is equal to cos alpha del w del x plus sin alpha del w del y. Now, to find del by del t, we only substitute or only change the alpha. So, because the normal direction and tangential direction are mutually perpendicular. So, if I substitute alpha equal to pi by 2 plus alpha or 90 degree plus alpha, then I get simply del by del t as this operator minus sin alpha del w del x plus cos alpha del w del y. So, substituting m n t that we have obtained from tau n t after integrating across the thickness, and then differentiating it, that means you use this operator, we will be able to get the expression for this second term, and q s term is already given here, q s equal to q x cos alpha plus q y sin alpha, and q x and q y expressions are given written here. So, you have to substitute and write down the full expression for the curved boundary. Okay. So, let us now go to the fourth problem. Fourth problem we will go here, we find out the picture. So, fourth problem is to find the distribution of internal stresses in a plate and show its variation along the thickness with reference to the middle surface. Okay. So, we have a say rectangular plate. Okay. So, I have shown a part of the plate, okay, a part of the plate subjected to load q, and suppose this is my Cartesian axis x, y and z. Okay. So, along the middle surface, let me show the middle surface. I am showing the stresses this along the x direction, normal stresses along the y direction, and then tau x y, tau y x here, tau y x, and here tau x y. Other stresses are shear stress, though we neglected, let us find the expression also, and then When the tau xz, tau yz are considered, this is not a thin plate problem, but let us find this from the first principle. Okay. Now, sigma x is known to us, it is equal to minus E into z 1 minus nu square into curvature this that we have derived earlier. Okay. Now, we also know the expression for m x. So, m x is minus d and this curvature. So, this term can be written as 12 m x by h cube into z. Now, why it is 12 by h cube? Because in the denominator h cube by 12 was there, and if I take a unit width of the plate, 1 into h cube divided by 12 is nothing but moment of inertia of the plate of unit thickness. So, you can see its similarity with the beam. Okay. So, that means the stresses varies linearly. If I measure the stresses from the middle plane, then it varies linearly with z along the depth. All right. So, h thickness is known and the quantity m x that will be found out, and then you can find the variation of m x. Similarly, we can find the variation of sigma y. Variation of sigma y is this. Tau x y you can similarly find. Tau x y is minus E z 1 plus nu del square w del x del y. Okay. Now, what we know that m x y is nothing but minus d 1 minus nu and twisting curvature. So, based on that we can simplify it and bring it in terms of m x y, twisting moment. So, twisting moment m x y is responsible to produce the shear stress tau x y. So, three expressions are known, sigma x, sigma y and tau x y, and tau y x is similar, and you can see here that all the three stresses that we assigned for thin plate problem is linearly varying along the thickness. So, linear maximum will be at the when z is equal to plus minus h by 2. So, maximum value can be found out, sigma max is equal to 6 m max by h cube h square. Similarly, sigma this is say for example, this is x. Similarly, sigma max y is also found as, this is also x bending moment in the x direction. Similarly, this is bending moment in y direction. I am writing as a subscript to distinguish between the bending moment along x and y direction, and this is okay. Tau x y is directly maximum tau x y is again given as at z is equal to h by 2. So, 6 m x y maximum divided by h square. So, these are the quantities. So, readily we can know the variation. Let us find the variation of other stresses. Variation of other stresses we have to find out from equilibrium equation. So, let us take the equilibrium equation in x direction in general 3D elasticity. So, we have this in absence of body forces, this is written as like that, all right. Now, whatever we get in sigma x, tau x y and etcetera, we let us substitute. Our aim is to find tau x z. So, we substitute this is we found it as 12 m x by h cube into z. Then here we found it as 12 m x y h cube by z. Okay. So, this quantity remain now as it is. Okay. So, what we actually find it here from this equation, I can write as z, I can take common and 12 by h cube I can take common. So, I can write like that represents a moment of inertia of plate of unit thickness. Okay. So, there you can see that two things can be arranged like that, del mx del x plus del mxy del y plus del tau xz del z equal to 0. Okay. Now, recall the equilibrium equation, that is nothing but our q x. If you recall this, this is equal to q x. Okay. So, I can write like that. Now, I can write del tau xz dz equal to minus 12 q x into z h cube. Integrate this equation. Integrate this equation, we will be able to obtain the tau xz. So, after integrating, tau xz is found as minus 12 q x by h cube z square by 2 plus a constant c 1. Constant is a function of x and y, because we are integrating with respect to z. So, it will be a function of x and y, but we know at surface the tau xz is 0. So, at z is equal to plus minus h by 2, we get tau xz equal to 0. So, imposing this condition, we get C 1 is equal to 3 by 2 q x by h. Okay. Hence, the expression for tau xz, now I am writing here, the final expression here I am writing, tau xz is equal to 3 q x by 2 h 1 minus 4 z square by h square. So, this is very known expression. Suppose at z is equal to 0, we get the maximum shear stress, that is the vertical shear stress is 3 by 2 q x by h, that is shear force divided by 1.5 into nominal shear stress q x by h, that quantity is known. In a rectangular section, the maximum shear stress, the average shear stress, maximum shear stress is 1.5 times of the maximum shear stress. Okay. So, that expression we have obtained for tau xz. Now, if I want to find for tau yz, similarly I will carry out the integration of the second equation after substituting the value of m y and this. So, second equilibrium equation is del tau x y equal to tau x plus del sigma y into sigma y plus del tau y z into del z equal to 0. Okay. So, here again let us substitute this tau x y will substitute, tau x y is 12 m x by h cube into z, and this sigma y will substitute m x m y into 12 h cube into z, and this remain as it is. So, similarly, we can understand that ultimately we get an equation that del x m x plus del y m x y, this is m x y, okay. This is m y, and 12 z h cube can be taken outside, and then we have tau y z by del z, del tau y z by del z equal to 0. This quantity is known as q y. Okay. So, similarly after integrating, we obtain this expression for tau y z. I am skipping the steps because it is known to you from the previous integration. So, therefore, tau y z can be written as finally is 3 by 2 q y by h 1 minus 4 z square by h square. So, this expression we have written. Okay. So, all the expression we have written, and then next expression is remain, that is sigma z. So, third equilibrium equation, let us take this third equilibrium equation d tau x z by del x del tau yz by del y plus del sigma z by del z equal to 0. Substituting this value of tau xz and tau yz that we have obtained earlier, and we can integrate this quantity, that is if I want to integrate, then final expression that you will ultimately getting an expression of sigma after substituting this the known value that we have obtained earlier, you will get a quantity like that. And with that constant will be there T by 2 h 1 minus 4 z square by h square. So, all the value of tau xz and tau yz whatever I have obtained, I have substituted here and I have taken isolated q x and q y. So, this is nothing but the expression that we have obtained is minus q. Okay. So, minus q, this expression is minus q. So, then after integrating and the integrating and imposing the condition and imposing that at z is equal to minus h by 2, when the bottom is free from any load minus h by 2, this sigma z is 0. So, based on that we obtain this expression for final expression for sigma z as sigma z z or sigma z whatever you call 3 by 2 q by h, small q is the transverse load on the plate, z minus 4 by h square z cube by 3. Ultimately, after integration and substituting the constant, then you will get this is 4 z cube by h square into 3, 3 will be there in the denominator. Okay. Then a constant term q by 2 is coming. So, you can see now at z is equal to 0, that is at the mid plane, the sigma z, the normal stress, that is the crushing stress you can call it q by 2, but at z is equal to minus h by 2 it is 0 and z is equal to plus h by 2 it will be q. So, now I can show you the distribution fully for all stresses. Okay. So, let me draw the plate. Okay. So, this is a part of a plate subjected to distributed load q, and let me draw the stress distribution in a different color. Okay. So, first this is the x axis, this is y axis and this is z axis. Okay. So, we have this sigma x, variation of normal stress along the x direction. If this is the neutral plane, it will be like that, linearly varying 0 at this center and this is. So, this is the variation of sigma x, compressive at the top and this. Okay. Then if I want to draw the variation of tau x y, let me show the variation. Of tau x y in a different color, so that you are not confused. Okay. So, this is the variation of tau x y. Again this is your what is called, it is linearly varying. Okay. So, on the other side also you can plot like that, there is no difficulty to plot this. Okay. On the other side you can show this, the variation of this along the middle plane. Okay. This is sigma y compressive, and this if you want to see this variation of tau x y, it will be similar but let me again show it, there is no harm in showing 2 times. So, you will get this variation as like that. Okay. But interestingly, you will get the variation of these other 2 stresses, that is similar to your beam shear stress, okay, that we get. So, here if I want to draw this tau x z, it will be parabolic and maximum here. Okay. Similarly, if I want to draw the tau y z, it will also be parabolic and maximum here. So, this is tau y variation of tau y and tau x y or tau y x. This is the variation of tau x z and this is the variation of tau y z. And for this sigma z, if you want to see the variation of sigma z, because it will be clumsy, let us show it separately. This is the plate portion, okay. This is the middle plane, this is h by 2, this is h by 2. So, here you will get the variation is like that. Here you will get this value q by 2 and here it is q and here 0. So, this shows the variation of this axis. Okay. Last problem let me see, and I will give the hints and it can be solved. Okay. In the assignment problem I will give the solution and you try the last problem. Okay. Thank you.